Okay, we will begin. It's 6 o'clock, so we are ready to go. So, good evening and welcome to the 5th event in our 2022 speaker series, Surprising Science, Borrowed Ideas Leading to Unimagined Consequences. I would like to acknowledge and pay respect to the traditional owners of this land on which we are this evening, the Ngunnawal people. It is upon their ancestral lands that the Australian Academy of Science is built. As we share our own knowledge, teaching, learning, and research practices, may we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of this country. I am Professor Nanda Dasgupta. I am a fellow of this academy and one of the conveners of this series. Also joining me to convene this series is Professor Drew Evans from the University of South Australia. And as a departure from our usual scenario, Drew has traveled in person, as have the two other speakers. So this is a fully face-to-face for those who are in this audience series, or this lecture. So welcome to the Shine Dome, Drew, and it is wonderful to have you here in real life. So I'll hand it over to you.
Thank you. So thank you, Nanda, and it is fantastic to be able to travel over here and partake in this event. Apologies to those online that I'm not broadcasting from my spare bedroom, as most people do in the current climate, but it's fantastic to be here in the Shine Dome for this evening. And thank you to everybody who's here and online for joining us for what's going to be a fantastic evening of talks. So tonight we will hear about some surprising science about lightning. We have Dr. Hannah King and Dr. Emma Lovell, and they're going to no doubt surprise you and inspire you by some of their specific research in and around lightning. But before we hear from them, some very important things that we need to take into consideration. If you would like to join in part of the conversation, especially to our people who are joining us online, please jump on Twitter and use the hashtag #SurprisingScience. For those of you that are here, please don't turn off your mobile phones, but just switch them to silent, and you too can join that conversation. Now, questions from our online audience, you'll be able to scan the QR code that will take you to a place where you can then put in your questions that we will then be able to work through in the Q&A session at the end of both of our speakers' session. For those of you who are here in the Shine Dome, you'll be able to address the microphone and ask your questions directly to our speakers. So, without further ado, let's hear from our first speaker, Dr. Hannah King. So Hannah is based at the Swinburne University of Technology within the ARC Training Centre SEAM, so Surface Engineering for Advanced Materials, and is developing the next generation of lightning protection devices known as air terminals. So to hear more, please welcome Hannah to the stage.
Thank you everyone for having me. Okay. So I'd also like to acknowledge the traditional owners of the land in which the Swinburne University campus is placed, and that's the people of the Kulin Nation. So just a little bit about me to start. So I completed my PhD in chemistry from James Cook University in Townsville. I'm currently working as a postdoc researcher at Swinburne University Technology, and I work within the research and development team called SEAM. So that's a bit different because most of my colleagues are engineers, but I'm one of these crazy chemists. So it seems a bit of an odd match, but there's a reason for it. That story starts here with this company, Lightning Protection International, also called LPI. Essentially what they do is they make sure scenarios like this do not happen. So they try to protect people and they try to protect property from lightning. So we're talking about lightning. How does lightning occur? Thunderclouds roll in, and then 95% of the cases, you'll get a negative charge built up at the bottom of that thundercloud. And what that's going to cause in the ground is all the negative charges are going to be repelled and the positive charges are going to be lifted up towards that cloud. So that not only happens in the ground, but it also happens at high up and pointy places, so at the tops of rooftops and the tops of trees, or if you're in a boat in the middle of the ocean, right there. At some point, you're going to get the positive charges reaching up and the negative charges reaching down, and then that is the lightning strike. So I've coloured this in here, grey in here, because we can't actually see this electrical charge. What we see is the plasma, which is formed by this electrical charge. So what happens is that electrical charge is so hot, it's about 10,000 to 30,000 degrees Celsius, and it heats up that air. So that air, where it goes from normal molecules, it heats it up so much that you start to strip those electrons from those molecules and atoms. So then you get these ions floating around with these negative charges, and that's what a plasma is. So that's what we see when we see a flash of lightning. So it's not just a cool thing, lightning, it's obviously very dangerous. So you want to protect people, you want to protect property. So the best way to explain how we do that is to think of the Empire State Building. So most people know Empire State Building, tall building in the middle of New York City. And at the very top, there's a very long spire. Okay? What's at the very top of that spire is a lightning rod. And that lightning rod is attached to a down conductor, which is just a big thick copper cable, which will conduct electricity, and then that goes into the ground. So what happens? The thundercloud comes rolling in, lightning strikes, all that electricity goes down through that down conductor, and then it gets dissipated into the ground. And that's made the lightning safe. So we can do the same thing on our little house. You can stick a lightning rod on your house, then the electricity can go down the down conductor and be dissipated into the ground. And then the little man is still happy. Nothing's happened to him. He's very safe. Okay? So the company I work for, LPI, make basically the best version of this possible. Okay? So they make these lightning rods here. Okay? And you know that they believe in their product because they have one on their own building. Okay? So this is what it looks like. Okay? So you can mount it on the top of the building or the top of the spire, but again, you want it at a high up pointy place. Okay, so you can see other examples over here. So this is the displaced persons camp in Bangladesh. So again, just on top of a large pole. And then you have one on a police boat in Singapore. Okay, because again, if you're on a flat ocean, the most pointiest thing is you. That's where the lightning is going to strike. Happens very often. Okay, but the problem we have with these things is pollution. And in the built-up urban environment, there's a whole lot of it. So you can see that you can get some from cars, you can get some from water drying on the surface. So if you have like salt water, then you're going to get all that salt precipitated out, NaCl. You have like dust, and you have particulates from open fires. You have pollution from manufacturing. You have smog, and all of this acts to dirty these lightning rods. Okay, so what effect does that have? Well, if we consider the two scenarios, the clean version and the dirty version, the thunder clouds come rolling in. The lightning strikes. If you have a clean lightning rod, then it's able to function perfectly normally. But there can be a case where this can be so dirty that it doesn't function properly anymore. In that case, you've no longer got a safe environment for your property or for people. So we really need to be able to clean these things. But you can see who's going to volunteer to clean these ones, right? The top of a long stick, get a ladder. So we really need that lightning rod to be able to clean itself. Okay, good idea. How are we going to do that? So we know that this base product is very good at what it does. We just want to add a bit of functionality to it. Okay, add a bit of functionality to what already exists. Let's just add another layer to the product. We want it to be self-cleaning, so we just add a self-cleaning coating. Brilliant. So we've got our problem, these dirty lightning rods. We've got our solution. Let's put a self-cleaning coating on it. How are we going to get there? Bit of R&D. So in this case, what happened, because this is an Australian-based company, the easiest thing to do, well, not easy, but what they did was they found a financial partner to be able to help them cover the cost of the research and to also contribute to the research itself. And they also found a research partner, which is where they found us at SEAM. Okay? So together, LPI, IMCRC, and SEAM, we all work together to be able to solve this problem and to be able to create a self-cleaning coating. So there's really 3 simple steps to doing that. 3 research questions, if you will. How will the coating clean itself? Question 2, how will the coating be applied? Question 3, what will the coating be made out of? Let's look at that first question. How will the coating clean itself? From the literature, you can see there's basically two options. One, it can be physically self-cleaning. So in this instance, you can see it's a super hydrophobic coating. So basically, the surface here, or the coating, it really hates water. But water loves itself. So the water will just ball up, and you'll just get these balls on the surface. And then those will roll around and clean up the particulates on the surface. Option two is you have chemically self-cleaning. So that means your coating must be chemically active. So you can see here, you just start out with methylene blue. This is just a dye. You can use it in aquariums, even in toilet blocks, to be honest. And then you can see over time, whatever their coating is, it's been degraded. I mean, I'm going to show you option one because it comes with cool pictures. Okay, so you can see the event here where the water balls up and then it rolls off with the particulates. And you see it cleaning the surface of this particulate material. And that's a self-cleaning coating. This is what it looks like when you actually look at it. You just see that this surface is super hydrophobic. It really hates water. Water loves itself. Water will just bead up and roll off. So a lotus leaf is, I think, still the most super hydrophobic thing out there. So this is why they base it off of a lotus leaf. Okay, so we've got these self-cleaning mechanisms. How are we going to apply this coating? Well, at my institute, Swinburne, we have SEAM, and SEAM specialise in a few things. They specialise in additive manufacturing, and they specialise in thermal spray. So this is thermal spray processes here. Okay, so it's kind of complicated, but also not. You have basically the material goes into the torch, then the torch does most of the work, in which it heats up the material and it increases its speed. And then all you have to do is put the thing that you want to coat in front of that torch. Okay, so it looks really cool because this is just a big line of plasma, and then you're just feeding the material into it, put the thing you want to coat in front of it. This is what it looks like when you actually do it. So this in particular is called HVOF, so it's just the type of torch it is here. And you can just see just a big long line of plasma, or just like an intense flame, a mega flame if you will. And the material is being fed through the back, it's being put into this mega flame, and then you just sweep in that torch over that coating, over that surface to create a coating. This is what it looks like on that millimeter scale. So within this mega flame here, you're getting those individual particles of material. They land in this molten state, then they cool down. Okay, so that's one splat or one little particle. All of his friends come along. Okay, so then this is what we're seeing now, where we're just doing one pass. And this is what you're going to get for one pass. You get all those individual particles. They're all going to cool. To create a coating, you just build up the layers. So I said that was kind of complicated, but kind of not. There's different types of thermal spray. It's an umbrella term. So essentially what we're doing, though, is the same thing. We're changing the temperature and we're changing the velocity of the particle. So we're just using the different types of torches to be able to do this. And to give you a point of reference in terms of what does particle velocity mean and flame temperature mean, what do these values are? This here is the speed of sound. We call it Mach 1. Right here is 2 times the speed of sound, that's Mach 2. 3 times the speed of sound, Mach 3. So we're going very quickly. We're moving these particles very quickly. And as a better reference, this is the speed of a commercial jet. This is the speed of Concorde. Some of you may know it. Some of you may have been around in that era. No offense. It's okay if you were. Okay? And this is the fastest plane we ever made, the Blackbird. So if we look at temperature, a flame of a candle, about 1,000 degrees, getting towards the center of the Earth, 2,900 kilometers down, we're getting around 3,700 degrees, and the sun, around 5,000 degrees. So this here is not even the minimum of what we can do. We can get up to like 28,000 degrees for this process. Okay, so as I said, it's an umbrella term, so all these are just the different types of torches. So you can say down here, you can have the cold spray version, so there's this torch here, it's a very large one. You can have wire arc, so that's over here. You can have the HVOF, so that's just like the one I showed you before. Okay, this one here is a detonation one. It's not very common, but still around. You can have flame spray, you can have plasma spray, so just different versions of it. And you can really just break it down into 3 categories. We have cold, warm, and hot. And to make it even simpler, if you think about superheroes, this one here is like the Flash. It goes very fast, but not very hot. This one here is Johnny from Fantastic Four. So medium temperature. This one, you're getting serious. You're getting the Iron Man effect here. So we have a way of making the coating. What are we going to make it out of? Well, for what we do, we're just using proprietary powder mix. So we did some research, we worked out what was going to work for us. Then all we had to do is just put it in the system and run it. So the problem we had, and the reason why I was here on this project as a chemist, even though I work with a bunch of engineers, which they're lovely, but they are what they are, is that all of these are high temperature processes. So you can see even for cold spray, we call it cold spray, but it's at least 500 degrees. You know, you're cooking in an oven at home, that's 200, 250 degrees. So all of these are high temperature processes. And the problem that we really had with our proprietary powder mix is that it was melting too much. So chemist comes along, tries to solve your problem. So essentially, what we're trying to do is we really love ice cream. We want to make that ice cream last as long as possible, but you're standing out in the summer sun, what are you going to do? Trying to save this ice cream. And that's what we try to do on this project. So we had a problem, which was these dirty lightning rods. We wanted to find a solution, so that was self-cleaning coating. We did a bit of R&D. So we found a self-cleaning mechanism, we found a way of making the coating, we found a powder mix that was going to work. And you know we did a good job because we're seeking a patent. Patent means money. Okay? So we're able to make something that was both novel and not obvious, and that's why we're able to seek a patent right now. So it actually feels like really amazing to be able to do something and see some science that no one else in the world has ever made. And that's what I find really exciting, is that you're seeing something that literally no one has ever seen. So, oh dear. I'd like to acknowledge the people today that I work with. So we work with an industry partner, so they're called LPI. We work with Paul and Franco, our financial partner, who's also involved with research. So we work with Matthew and Lydia with that. And of course, our team, our SEAM team within Swinburne University. So we have Professor Berndt, Professor Ong, Dr. Hocking, and Ludwig Wedemeyer is our PhD student exceptional. Thank you.
Thank you, Hannah. That was a very, very interesting talk, and hopefully people picked up on the irony there of using plasma to put down the coatings to protect us from plasma. It seems it's sort of the robots making robots kind of scenario. But I think a really nice point that you drew out there was, firstly, teams solving problems. So Hannah's a chemist working with engineers to solve a very practical problem of protecting us from lightning. But I think also seeing that connection of some quite fundamental research and thinking about how that fits in with manufacturing, and Hannah talking about filing patents. I think that's a really key thing to pick up on, and hopefully a lot of people in the audience were able to pick up on that little bit. Now, without giving away too much of the secrets of what's to come, I'd like to introduce our next speaker, Dr. Emma Lovell. So Emma is a senior lecturer in chemical engineering at UNSW in Sydney. Her research focuses on catalyst design for a range of environmental and energy-related applications. To hear more, please welcome Emma.
Thank you so much for inviting me here today to talk, and thank you for all of you for joining. I'd like to begin by acknowledging the traditional owners of the land in which we meet today, the Ngunnawal people, and I'd like to pay my respects to elders past and present and extend that respect to any Aboriginal or Torres Strait Islanders here today. This evening I'm going to talk about the life of lightning, and specifically on our work for catalysts for power to X. So first up, what is a catalyst? If you picture yourself standing at the foot of a hill and you want to get to a swimming hole on the other side, in order for you to make it over that hill, you have to essentially exceed the activation energy, required for you to climb that hill and walk down the other side. Now picture there's a tunnel being built in front of that hill in front of you. Instead of climbing over that big hill to make it down to the other side, you can walk directly through. This is what a catalyst does. It isn't changing a start point, it's not affecting your end point, but it is changing how much energy, or the activation energy, it is required to get to the other side. So on the other side of your hill, you're at your watering hole. And that watering hole can consist of water that might be in a state of a solid, a liquid, or a gas. We're all very aware of these three states of matter: If you apply energy to a solid, you'll end up with a liquid. You apply more energy with a liquid, you'll end up with a gas. Now, if you apply energy to that gas, you'll generate plasma. And Hannah's just gone through beautifully the background of lightning and plasma, so I don't need to go too much into the details. But essentially, plasma exists in a range of excited species. You have electrons and ions, radicals. You have vibrationally and electronically excited molecules. So that leaves us with the question, what is a catalysis researcher like myself here today talking about the life of lightning? Now, the answer to that question is in power to X. Power to X is the conversion of power, and in particular, the conversion of, that's me gesticulating, the conversion of renewable energy, variable intermittent renewable energy, into a form that we can store, transport, and use. So in this case, what we can do is take green renewable energy, take a range of different input molecules like CO2, like water, like nitrogen, and convert it into X, where X could be hydrogen. X might be synthetic hydrocarbons. X could be ammonia. These are chemical energy that we can store, we can distribute, and we can transport within our current energy system. So in order to take this variable renewable energy and convert it into X, we can use a range of different approaches, and a lot of them hinge on catalysis. So if we look at our catalytic conversions, we have reactants going into products, climbing that big hill that we saw before. If we add a catalyst bed, we're reducing the height of the hill. Now, what if we apply plasma to that catalyst bed? What we're doing now is taking our reactants and converting them into that range of excited species. In doing so, what we can do is essentially increase the energy of our reactants, thus lowering even further the height of the hill we have to climb to get to our products. Now, this is really beneficial because it means that plasma, or turning on this energy source, can be inherently compatible with this variable renewable energy. When the sun is shining, we can turn our plasma on. We can generate electricity from our solar panels and turn our plasma on. When the sun sets, we switch it off. Plasma is beneficial because it means we have this quick on-off capacity because we can apply it just over our catalyst bed. Instead of heating up large, big, centralized reactor systems, we can now move to smaller scale, decentralized systems, producing on-site, on-demand chemicals that are fit for purpose. Plasma localizes that energy source, and it also can simultaneously activate both the reactants and the catalyst, thus allowing to drive conversions under non-equilibrium conditions, or make conversions possible that wouldn't otherwise be allowable under the certain circumstances. Now, this is a really exciting area of research and why I'm here surprising you all with my science today. The problem with this plasma catalysis system is that there is a very complex and interdependent relationship between the reactants, between the plasma, and between the catalyst. So in this emerging field, we need to try and decouple and understand this complex system and try and probe the role of each of the different aspects so that we can understand and better design catalysts to capture this unique non-equilibrium energy input into the system. And so today, I'm going to talk about two of our group's research works into plasma-driven conversions, and that first example is for CO2 conversion. Now, I think we're all very aware of the harmful impacts that CO2 emissions are having on our atmosphere, looking at the catastrophic impacts of climate change. Can we look at ways that we can not just take waste CO2 and emit these anthropogenic emissions to the atmosphere, but actually convert them, utilize them as a tool in order to create other chemicals which we so greatly rely on? So in this work, what we looked at doing is taking carbon dioxide and reacting it with hydrogen. Hydrogen that can be created by green power to X, and in doing so, we can create synthetic natural gas or methane. Synthetic natural gas or methane can be used within our conventional infrastructure, and in this way, we can essentially capture CO2 and convert it into something which we already have the infrastructure around using. Now, the problem with this is that carbon dioxide is an incredibly stable molecule. It's very linear, triple bond, double bonds. Because of that, you need really high temperatures in order to drive the conversion of CO2 into methane. Typically, temperatures of over 300 degrees are needed. The problem is, as you start to heat up, you tend to make the reaction less thermodynamically favorable, and you start to make other unwanted side reactions like carbon monoxide through the reverse water gas shift reaction. So in catalysis, we call this selectivity. How much of the product we want, methane, are we making versus how much of the undesired product is carbon monoxide. So we thought maybe we can use plasma to start increasing the height of our hill or adding more energy to our reactants to make this conversion more favorable. To start off with, what we did was look at just heating up the system and putting in a pretty well understood catalyst for CO2 conversions. By using thermal catalytic conversion, we can convert CO2 into methane, but as you can see here, typically high temperatures are required in order to achieve that conversion. So now what happens if instead of heating up the system, we can apply plasma? Can we activate the reactants? Can we find a synergy between the reactants and the catalysts in the plasma environment in order to convert CO2 to methane at room temperatures or close to? So first, we started off generating plasma, just plasma by itself in CO2 and hydrogen. Plasma with some glass beads within the bed, plasma with just some alumina, a relatively inert metal oxide. And what you can see is, cool, with this system, we can convert CO2, but at relatively low conversions, less than 20%. Now, when we start to design and tune our catalysts to better suit the energy input from the plasma, we can then increase our conversion of our system really dramatically. So if we compare this conversion to the thermal conversion that we were able to achieve otherwise, it's essentially zero at the same conditions. That means that we would need to heat the entire system up to about 300 degrees to obtain the equivalent conversion that we are able to obtain now just by using that plasma energy input. When we started to look at the selectivity of the system, we learned some interesting things as well. When we just use gas or beads or just this inert alumina, we tend to make a lot of this unwanted side product of the carbon monoxide. Now, as soon as we put in even a tiny bit of metal into the system, we're able to effectively tune the selectivity of the system to produce pretty much 100% methane, just by incorporating the appropriate catalyst within the system. So what we did was try and understand this complex and interdependent plasma catalyst reactant synergy. And a really interesting thing about plasma is that the color of the plasma is dependent on the nature of the activated species that are present. That's why we have neon signs. So what we did was essentially utilize optical emission spectroscopy, or OES, to measure the color of the light that the catalyst emits. And by doing so, we were able to see that putting in a catalyst with a metal can control the plasma and the different species that we get, thereby controlling that pathway, making that selective methane formation. We also looked a little bit of the impact of the plasma on the catalyst, and what we found that not only was the plasma influencing the reactant gases, but it was also changing the way that the nickel was in, the form that it was in under the reaction conditions. So after reaction, the nickel size on the plasma decreased and the dispersion increased. So what we can see from this system is that we're able to selectively transform carbon dioxide into methane. By effectively attuning the catalyst, we can control not only the active species in the plasma, but also the nature of the catalyst itself and drive more selective transformations into something like methane. There are a range of different properties from the catalyst, not just the metal, not just the support, that you can tune and control, therefore driving selective transformations of CO2 into methane and other synthetic hydrocarbons. So the other example of plasma conversion I'm going to talk about today is nitrogen. So nitrogen is utilized to produce ammonia, and ammonia is one of the world's most produced industrial chemicals. The production of ammonia emits 1% of the world's carbon dioxide emissions and consumes 1% of the world's energy just by driving this conversion. The process that we use to produce ammonia hasn't changed since World War I. That process, it's predicted that without that invention, that half of the world's population wouldn't be alive today without it. Because using it, we can utilize it as a fertilizer to mass produce food. So the way that we currently produce ammonia is we take natural gas and we extract the methane, and then we react that methane to make carbon dioxide and hydrogen. We then take air and we use an air separation unit to produce nitrogen. We then react that hydrogen and nitrogen together to produce ammonia. Now, this process produces a really large amount of CO2, and a big part of that is because you need really significant temperatures, like 450 degrees, and 200 atmospheres in order to overcome the stability of a nitrogen molecule. So nitrogen itself has a triple bond, it's a very stable molecule, and so therefore it needs a lot of energy to overcome and to transform it into something valuable. So what we did was look at the way that nature converts nitrogen. And as Hannah just went through, lightning is a big part of that. Lightning can activate air. When it activates air, it can convert nitrogen into a range of reactive species, such as NOx. And so that's what we did. In the lab, what we did was take air and water and use plasma or generate lightning within a tube to produce NOx. This NOx in solution is a mixture of nitrate and nitrites, which are soluble and much more reactive than the nitrogen molecule itself. From that NOx species, we can then electrochemically convert it much more easily into ammonia. Now, the benefit of this is that both of these systems can be powered by this variable renewable energy, fitting in with that power to X space that I spoke about previously. So what do each of these sections look like? In the plasma process, what we do, and working with our wonderful colleagues at the University of Sydney, we develop systems that could essentially activate and generate plasma at the interface between air and water. And in doing so and in controlling so, we can then produce a range of activated nitrogen species in the gas phase and in the liquid phase. And these species, and again measured by the light and the color that comes off the plasma, we could then control essentially how we produce these nitrate species. And we can reduce the energy required in order to produce these nitrates as well. Now, once we have these nitrates and nitrites, we can then take them and electrochemically convert them by designing electrocatalysts into ammonia directly. So we took some copper, not dissimilar from the copper that's coating the beautiful shine dome. We produced some nanostructures on the surface of copper foam, and from that we could take our plasma-activated water and electrochemically reduce it into ammonia. Okay, and in doing so, we can basically start with air and water. We can get the hydrogen from water. We can use plasma to transform our nitrogen into a more active species. And from that, we can produce ammonia without fossil fuels, without the large-scale manufacturing processes, without the high temperatures and the high pressures, thus allowing us to produce ammonia on-site and in an on-demand fashion. So we took this even further, and some of you might be aware that NOx is quite a harmful pollutant. And so can we potentially capture and leverage NOx that's already in the environment? Can we take NOx from power plants and from wastewater and also utilize that to supplement our plasma-produced NOx? And so in this work, what we're able to do is further design and tune the atoms on a surface of a copper catalyst by using plasma. So we can use plasma as a tool to induce defects. So in catalysis, imperfection is beauty. When we plasma treat a catalyst, we can start to take oxygen out of the sample surface. And as we remove that oxygen, we can then increase how much our reactants want to start interacting with the surface. So in this work, what we're able to do was essentially vary the plasma treatment time of our copper electrodes. We could then use that as a tool to tune and control the performance and the selectivity of our materials and allow us to essentially change how effective our catalyst is in producing ammonia under these conditions. So in our work, what we really try and do is convert power, and in particular, variable renewable energy, into X. So today I spoke about a couple of X's, one of them being methane, another being ammonia, and ways that we can utilize conversion systems, not just electrocatalysis, but also plasma catalysis, and essentially capturing lightning as a way to drive selective conversions. So as we move toward an electrified system, we really need to shift our thinking and our ways towards storing and distributing and transferring energy. So I'm going to end on my favorite quote from a book a few years ago, which was that clearly the world does not lack energy. All we lack is the knowledge necessary to harness and convert it to our needs. And just before I wrap up, I wanted to leave a few moments to acknowledge all of the wonderful people who have contributed to this work. I work in the PartCat research group, which is led by Professor Rosa Mal and Associate Professor Jason Scott. The nitrogen work undertaken by Ali and Diane, which was Jing, was the main PhD student who was really leading that charge. The CO2 conversion work of PhD students Farhan and Zafran, and also our collaborators, Professor PJ Cullen from USyd and Kostya Ken Ostrakov from Queensland University of Technology. Thank you.
Thank you, Emma. And how fabulous to hear about the work of Hannah and Emma. I was sitting there looking at the bigger picture and thinking, wow, using plasma to protect us from catastrophic effects of plasma, as Drew pointed out. And Emma using the ideas of lightning and the processes of plasma to find greener ways for creating chemicals, which serve us as food to keep us going on the planet. So, and to take your thing about world doesn't lack energy, world clearly doesn't lack ideas. It is how to harness them and put them to use for the benefit of our planet and ourselves. But what struck me is both the speakers were talking about immediate problems, but all the discoveries were underpinned by fundamental science. And I think that is the connection which many times is missed in the world and in the nation and among the political and other dialogues that we have. That link between fundamental science and applied science is very close. And if we lose, it is not one at the expense of other. So I think that was very, very beautifully highlighted in Hannah and Emma, your works. So I think we will open the floor to the questions, and from the audience here, as well as those who are joining us online. So Hannah, if you could come up, and for those online, can you please submit your questions by scanning the QR code on your screen? And those in the audience, with the great treat, everyone being here, please come up to the microphone to ask your questions. And we will do the same dual act. Drew, you will, it's a competition, so, okay, online versus here. Okay, right, so do you have any questions there?
Sure do.
Oh, maybe I should take over your role at some point. Okay.
So here we've got a question for Hannah, but I think equally we could probably ask Emma as well. But this question starts out by firstly thanking you both for such entertaining talks. most people will understand the impacts of lightning strikes, and Hannah, you described it very nicely about some of the catastrophic things that can happen. Both of you work with lightning on quite a daily occurrence in your labs. So the question is, have you ever set fire to your labs working with lightning?
What do you want to admit to?
Work and health and safety won't let them do
Yeah,
it.
we've got to be careful here.
I'm happy to start.
You go crazy.
So when you do this thermal spray process, you don't want to be in there with the torch. So perfect job for a robot. Then you have to program the robot. That can go haywire, okay? So there has been instances where the robot doesn't do what you want it to do, and you thought, oh, that's not what I programmed it to do. But that's why you generally start the process when you do the thermal spray. You do it with the torch off, you run the program with the robot, and you make sure it does what you want it to do. So in that case, that's the worst thing that can happen with us, is that the robot doesn't do what you want it to do, and it moves the torch in a direction you don't want it to go. And so we run the robot without the torch on, and we put the whole thing in a spray booth, so it's insulation protected, so it's also fireproof as well as soundproof, because it can be a very loud process. And in that way, we don't get the lightning happening in the lab specifically.
Yeah, we utilise a non-thermal plasma, which means our plasma is essentially at room temperature, so the risk of setting to fire to things is relatively low. The catalysts that I spoke about in that last slide, they were made by a flame spray process. So in that case, we are purposely setting fire to things, and it's only like 3,000 degrees, so on Hannah's scale, that's relatively cold. But in that way, we're doing it safely.
Okay, from the floor here. Going once. Okay, you carry on.
All right, we'll go to another one online. So Emma, this is a question for you. So this question is focusing a little bit on, I guess, the scale of where you see your catalysis system being deployed. Is this something that we might see in the future deployed on household solar systems, for example?
Yeah, I think it really depends on specifically the application that you're looking at. So we definitely hope and envisage that the ammonia piece would allow farmers, for example, to produce their own ammonia on-site and on-demand being powered by solar. That's still a little way away. We're at lab-scale prototyping system, but the goal for that work is to really allow that distributed on-site, on-demand production of specific chemicals that are required in specific circumstances. So for the ammonia piece, absolutely. The CO2 piece is a little bit different because your input in that case isn't air and water, it's concentrated carbon dioxide. And concentrated carbon dioxide is going to come from point source emissions, which means that likely they aren't going to make sense to have those units in your backyard because you won't have a point source emission of CO2, but could you couple them to a power station, or you could couple them to a concentrated CO2 source like in the future through direct air capture? Absolutely. So it would depend on the system and the input to the X that you're looking to produce.
Thank you.
Come on, the floor. Pressure's on.
Just that good.
Well, I'm going to ask you a question then. Hannah, so because when you said cold plasma, it was still high temperature. So does that limit, that kind of technique, does that limit the kind of material that you can put a coating on?
So the way that you choose which thermal spray process, so it's an umbrella term, thermal spray, and then you have all those different types of torches. And basically you have the choice of what you're putting in and what you're spraying it onto. And those two things are really what's going to govern which torch you use. So if you want to put, on a steel substrate, for example, you can put titanium. Well, if you put titanium in a plasma torch, then that's just going to oxidize it. And so you're just going to get titanium dioxide on your surface. So you would use a thermal spray process which doesn't go through that oxidation process, which would be cold spray. So there's companies that do that. So that's actually another industry partner that I work with called Titomic, and that's what they do. They do cold spray of titanium. So it's really, you can basically spray onto any substrate for all of the techniques, but it's really what you put into it. That's really going to depend what torch that you're going to use. Because sometimes you want it to get really melty, so you use high temperature, and sometimes you don't need it to get melty, you just need it to be able to stick to the surface, in which case you use the cold spray, which is worked by plastic deformation. So instead of heating it up to melt it, you just make it go 3 times the speed of sound, and then the particle's not solid anymore, it becomes all plastic, and you get that plastic deformation. And then so when it hits the surface, it basically acts like it's hot. And so that's how it sticks to the surface. All its mates come along, and then that's how they all stick together, and then you just build up the coating like that. So it's really what material you want to put on it is mostly the governing factor of which torch you're going to use.
Drew.
So this is, I guess, a question for both of you. And Hannah, you described really nicely about lightning that we get out in the environment and the clouds rolling in and the charge build up. I guess for both of you, what do you make small clouds? Well, what's the equivalent of clouds in your system to generate that charge?
So if you take one torch, for example, like a plasma torch is the most direct one because it's making a plasma. All we have to do is to be able to we run argon through the torch, we put a very high voltage over that argon, and then those argon atoms then become very excited, and they're so excited that the electrons come out of the argon atoms. So then you have ions of argon, and then you have the electrons floating around, and then that's when you create the plasma. So then all you have to do once you've stuck that high voltage through it is just put a lower high voltage through it to sustain that plasma. And so you don't actually have a cloud, you just need to create that scenario where you have the ions and then the floating electrons that can't rejoin their atoms, and then that will be the plasma. So that's what happens in my case.
Yeah, I wish we could create clouds in the lab. I think that would be way cooler than what we do. But what we work with is a dielectric barrier discharge non-thermal plasma. So essentially what that means is you have 2 dielectric barriers, you have 2 chunks of glass, and you have a high voltage electrode and a ground. And if you pass that gas through, if you apply enough energy, enough power, you can start to generate a plasma. Depending on the gases that you have present, that will dictate the excited species. So argon is a bit easier, argon and helium are a bit easier to break down than something like CO2 and nitrogen. So you have to control the gap between your electrodes and the thickness of your glass and the gas in there, as well as the energy that you have to input in order to break down the gases and then generate that plasma.
Fabulous.
Yes. Yes, please. Thank you. I hope that's a start of a flood. Hey?
Okay. I think I'll just speak like that. Thanks for the really lovely talks. My question, I have 2 questions actually, both either of you can answer, but I think Emma, I wanted to ask about the catalyst. I think I might have missed it. Do you have good regeneration rates for the catalyst that you're using in the carbon dioxide to methane conversion?
It's a great question. So we don't see any change in conversion or performance with time. What we do see, and when we initially started running these plasma conversions, we were really excited to run the conversions at room temperature. Can we take CO2 and convert it at room temperature? Amazing. What happens when you do that is you make a heap of water with the reaction. And when you have a room temperature catalyst bed with a heap of water, you don't necessarily deactivate your catalyst, but you do fill up your bed with water, which means gas isn't passing through and your plasma is not generating properly. So when we started to heat up the system a little bit just to make sure that water stayed in the vapor phase, we were able to maintain conversion, turn the plasma off and on. Something we're really interested in at the moment and looking at is how does the catalyst change in plasma? We can see it changes a little bit. That doesn't affect the performance, and we can turn it on and off and it maintains the same. But understanding how different materials might vary is something that we're looking at now and seeing if we can't capture some of that change and use it as a way to more effectively design materials.
Thanks. And the other question is just my curiosity because I'm a biochemist. And so with the methane that you will generate from carbon dioxide, what types of uses would you envision?
So methane, initially the motivation was twofold. One is that can we take CO2 and essentially make natural gas so that methane could be fed and utilized within our natural gas infrastructure. The other motivation was that it's a relatively simple reaction and it's a really complicated system. So using the simpler CO2 conversion reaction helps us generate that understanding, and then in future looking to produce more valuable higher hydrocarbons from the reaction like methanol or ethanol and other things is going to be a focus.
Yeah, because I was thinking methane itself is also even worse than carbon dioxide.
Absolutely.
So you need
You don't want to be emitting that
yeah,
methane. The
yeah.
idea is to use it within our
The good
infrastructure.
use,
Yeah.
yeah. Thank you. Thanks for that.
That was going to be my question, why methane is so bad, right? But now when you're talking about alcohol, that's a different thing altogether. Right, any other questions? Drew, you go.
Thanks, Nanda. So this is a question for Hannah. So you've spoken a little bit about these plasma coatings and so on. The question here is starting to think about how that gets used in making different products. Is it an expensive process? And where is, I guess to paraphrase the question, where is plasma coatings used already, and what sort of scale of product could you potentially use it on?
So it's basically a process where you put coatings on things. So there's whole companies that have different torches and they just put coatings on different things. There's a really good one, I think it's called MCC over in New Zealand. I can't remember what the company's called. I think it's called MCC, but I can't remember the full name. And they have different torches and they just coat different things. So if you've been on an aeroplane, you have been around these coatings because it's only like a 200 micron layer that is prepared by a thermal spray method that is saving that engine from getting too hot and blowing up. So it's everywhere, but you just don't know how it's made. So it's usually coatings that are quite thin, so 200 microns or thinner, even that, 200 microns. It tends to be that sort of region. It's just like another example is in New Zealand, that MCC company, they had a bridge that they put in a very, very corrosive environment. So they wanted to protect that steel. So on the pilar or the pylons that go into the water, they coated that whole pylon with aluminium. And then you've got something that's going to create a passive layer, aluminium oxide, and that's not going to corrode anymore. So they just have these, I have a problem. We have thermal spray, we fix that. And there's whole companies that are dedicated to it. So there's other ones that I work with. I work with two other industry companies. So one of them is Titomic, which they do the cold spray with titanium. And then there's another one that I work with is DNT. So they take hydraulic cylinders. So where you have like those massive, you have the toy trucks that you give little kids to play with, and they open up the back and then it all dumps out the back. So the big version of that in the mines, to be able to lift up that back, there's a big hydraulic piston. So inside there, you need to be able to repair those. Because to be able to buy a new one takes a lot of time, takes a lot of money. So they generally repair them. So the kind of extreme version of this is like a laser coating. So they call it laser cladding. It's generally under the umbrella of thermal spray, but basically there's whole companies that are dedicated to being able to just repair things and coat things. And that's what's really good about these thermal spray processes, is that as long as you have that line of sight, then you can coat it. Doesn't matter what shape it is. So, you saw that our special lightning rods were a curved shape. We can do a curved shape. You've got a cylinder that's a pylon that goes into the ocean. We can coat that. So you just have to think of a clever way to make the robot do it, though. But generally, you can just coat anything.
Excellent.
Okay, Drew, you're winning. I don't like your face doing all those. Come on, we have to have some questions from here. Otherwise, Drew, you go.
Well, we've got a question here online, and we're just going to change pace a little bit with the questioning here. And this is really thinking a little bit more about science in general and careers in science, and it was something we were talking about prior to being online. But from both of you, firstly, what is your advice for young scientists out there? And probably the big question, are there careers in science?
You want to go?
I can go first. The advice that I will give is the advice I give all of my undergrad students, which is try everything. Every opportunity that comes up, put your hand up to, give everything a go. You won't know what you enjoy, you won't know where your passion is until you give it a go. And even if you hate the experience, you'll at least know that that isn't a path for you. So that's my advice. Are there careers in science? Hell yeah, look at all of us, it's done. It's an easy one.
Yeah.
Yeah, so my general advice is have hobbies. Because people generally say, oh, I'm really interested in computers, but I really like engineering, but I really like chemistry. Well, you know, everything's like, we put these boundaries on things to say, you study chemistry, you're a physicist, you're a mathematician. But when you get out into the world, you're like, hang on, there's no boundaries to this. Everyone does everything. So if you've got a hobby that's in, you know, computing, and you also like science, you know, there's a whole bunch of people out there who do modeling, right? If you have an interest in, you know, biology and, you know, plasma spray. You know, I've worked on projects and they make coatings for hip implants. You know, it's okay to have hobbies and to actually have your hobby be your work. And it's okay that you have very, very different interests, because there's probably something out there that suits your needs. There's lots of the collaboration and, you know, interdisciplinary work to be had. In terms of like, is there jobs in science? It's always a fear that people have of, oh, will I get a job? Because you're going to university, you want to have something at the end of it. But generally, I always just say, you just have to keep doing the things that you want to do. And you just sort of have to say, okay, am I enjoying what I'm doing? If it's yes, then keep continuing that. And then go to the conference, go to talk to this person, go outside and try this experiment, or you know, go to this lab class and just try the different things that you want to do, because you're probably going to meet someone, or you're probably going to stumble across something that you like, and you're like, I didn't even know this existed. And there's lots of things now. You think about, you know, there's people out there who do TikTok for a living. That didn't exist 5 years ago. There might be things that you're interested in now, and it's just not invented yet. So just keep working towards something, and you just do that by just keep doing the things you love doing. So that's my general advice of, will you get a job? Yeah, probably. It'll be fine, right? Just keep doing things that you do, because this is your life. It's not just a job. You've got to enjoy your life, and you know, your work is, you know, a big part of your life. So just keep doing things that you like doing, keep doing the jobs you like doing.
Thank you.
It's funny, that is exactly the advice I was giving one of my staff just 2 hours ago, that you have to do what you like, and if you're passionate about it, you will excel.
Yeah, I mean, it's your life.
Yeah.
You spend so much time at work, it'd be awful if you didn't like it.
That's right.
Just live your life.
And a science career doesn't mean it's only working in the university. I know I'm a nuclear physicist, and students who have gone on to genetics because of the large data sets and modeling, and you would never think that.
It's just like another one that's a really odd link that you think, oh, how does that happen?
Yeah.
Is that actuaries and people who work in banks, they love to hire physicists because
Yes.
they're really good at data analysis and they're really good at those fine details. And you think, why is ANZ hiring a physicist?
Yeah.
And they do it all the time.
That's
There's almost like this channel between, like, if, for example, my university and like ANZ or NAB, and they just take all the physicists, and you're like, why are the physicists going to a bank? And that's why, because they just have that skill set of attention to detail and numbers and being able to understand complex problems, and you're like, oh, that's that crossover.
Yeah, how do you
You think, how does that happen?
take a complex problem and break it down into smaller bits so that you can solve each one of them?
It's a problem, it's
Yeah.
numbers. Oh, we're just on different sides of that, money versus science.
Yeah. Except when as one of our postdocs came and said, oh, well, this bank is offering me this much money, can you match it? It's like, no, mate. So I think I think we are getting very close to the time, unless someone from the floor is really feeling brave to come up to the microphone. I'm sure you have more questions, but I think we have to stop
I've got
soon.
hundreds.
No, we have to wind down. Okay, right. Okay, we will put it on. There was an email given, so maybe people can direct it to them. So I think we will stop here. So thank you all for the great questions, particularly the online people did well there. But that's all we have time for. There are many more questions that they could answer, which just shows the interesting talks and the ideas that Emma and Hannah were able to convey. So a big thank you to both of you for joining us tonight, and to my co-convener Drew, who is able to join us in person this time. We also would like to thank Jira at GX Station Wines and the Shine Dome team for refreshments earlier this evening for those who are here in the Shine Dome. And thank you all for joining us tonight, and we hope to see you again in the next installment of Surprising Science on 13th December. And just prior to Christmas, and in the spirit of all the things being decorated with light, we will have a talk about visibility and invisibility of light. Thank you very much, and have a good night.